In this next section of Chapter 4, we're going to introduce further concepts of vector spaces. In this case, look at two specific kinds of subspaces, null spaces and column spaces, associated with matrices. So the null space of an m by n matrix, we're going to be given a matrix and talk about something with that matrix, is going to be the set of all solutions to the homogeneous equation AX equals 0. And it might be very useful to go back and check out an earlier section, section 1.5, in which we introduce the homogeneous equation. And a lot of what we're going to do is what we did in that section. So the null space, we're going to write that as NUL of A, is going to be the set of vectors x in Rn such that AX equals 0. It is all the vectors that satisfy that homogeneous equation. Now the null space of an m by n matrix A is a subspace of Rn. Equivalently, the set of all solutions to the system AX equals 0 of m homogeneous linear equations and n unknowns is a subspace. In order to show that it's a subspace, we need to show that those three properties, the 0 vector that's closed under addition and closed under scalar multiplication, are satisfied. And we'll do that on the next page. So here we have the null space of A. We've got to satisfy these three properties, the first one being the 0 vector. So we need to show that the 0 vector is in null of A. But since A times 0 is 0 itself, then that means that 0 is in the null space of A. Trivially, we always have this trivial solution to the homogeneous equation. What gets interesting is when we have something more than just the trivial solution. We need to show that this is closed under addition. So that is, if I have two vectors in the null space U and V, that their sum is also in the null space. So since U and V are in the null space of A, that means I have that A times U is equal to the 0 vector, and A times V is equal to the 0 vector. And I need to show that A times U plus V is equal to the 0 vector. Using some properties of matrix vector multiplication, I can write A times U plus V as AU plus AV using the distributive property. And then since AU is equal to the 0 vector and AV is equal to the 0 vector, then we have that this is all equal to the 0 vector. So therefore it's closed under addition. And finally, we need to show that it's closed under scalar multiplication. So if I take an arbitrary vector u in the null space and an arbitrary scalar c, I need to show that c times u is in the null space. And again, I will look at and try to show that a times cu is equal to 0. So a times cu, I can bring out this scalar out in front to write it as c times au. And since a times u is equal to 0, that's from it being in the null space, we get that this is going to be equal to c times 0, which is equal to 0, and therefore we're closed under scalar multiplication. So since I showed all three of these properties, for any matrix A, the null space of A is going to be a subspace of Rn. To determine what is the null space for a certain matrix, or to see what an explicit description of the null space is, we're going to go do a very similar thing as we did in section 1.5. We're going to row reduce the matrix and look at the solution to the augmented system. So here is our matrix A. Find an explicit description of null space of A, where A is this 2 by 5 matrix. So A is a 2 by 5 matrix. And I point that out because we're going to be looking at the dimension and see how that has to do with this dimension, this 2 by 5 dimension of the matrix. What that has to do with the null space and what we're going to introduce the column space later. So first thing we're going to do to solve this equation, AX equals 0, is we're going to look at the augmented matrix. That's the matrix with this bar and then 0, 0. And if I row reduce that matrix, I could take -2 row 1 plus row 2 into row 2, do some other kind of things, maybe take 1/3 of row 1 into row 1. I get this matrix in row reduced echelon form. And from there, I'm going to be able to solve this by identifying the free variables. So first, it might help to identify the pivots in my matrix. Those are those two ones right there. And that means that x2, x4, and x5 are my free variables. If I take this row reduced echelon form matrix and I write this in equation form, this will give me x1 plus 2x2 plus 13x4 plus 33x5 is equal to 0, and x3 minus 6x4 minus 15x5 is equal to 0. And then I'll be able to write it as a vector x equal to x1 to x5. We know that x2, x4, and x5 are free. So we can just write them as x2 equals x2, x4 equals x4, x5 equals x5. And then just rewriting those two equations to solve for x1 and x3, we get x1 is -2x2 minus 13x4 minus 33x5, and x3 is 6x4 plus 15x5. Then I can write my solution as the linear combination of vectors corresponding to my free variables. If I take those free variables out, I get x2 times the vector -2, 1, 0, 0, 0, x4 times the vector -13, 0, 6, 1, 0. Again, these come from the coefficients corresponding, so -13, 0, 6, 1, and 0 come from the -13x4, the 6x4, the 1x4, and then 0 for the other two. And the same thing for x5. And another way we can say this is that the null space of A is equal to the span of those three vectors. Now we already know that the null space is a subspace, but even right now we could show this is a subspace because it's the span of vectors in R5. This is a subspace of R5. And that 5 came from the second coordinate here in that 2 by 5 matrix. So, finding the null space boils down to doing what we did in section 1.5, solving a homogeneous system. So let's take a look at this subspace a little bit more. So here the spanning set of the null space is automatically linearly independent, and that's going to be true regardless of what we have for the null space. And the reason that's true is if I look at a linear combination of those vectors and set them equal to 0, I need to have C1 equal to 0, C2 equal to 0, and C3 equal to 0. And let's see why that's the case. C1 is 0 because if I look at the second entries here, that's going to give me C1 times 1 plus C2 times 0 plus C3 times 0 is equal to 0, or that C1 is equal to 0. I can do a similar thing for the fourth entries corresponding to the second free variable here, and that will give me C2 equal to 0. And I could do a similar thing for the third free variable here, x5, and that will give me that C3 is equal to 0. And since I'm always going to have these ideas with the free variables, I will always be able to have that these spanning vectors are always going to be automatically linearly independent. Also, if the null space is not equal to just the 0 vector, that means that there is a non-trivial solution to AX equals 0, then the number of vectors in the spanning set is equal to the number of free variables in AX equals 0. In the previous example, we had 3 free variables, we had 3 vectors in our spanning set. Note that if there are no free variables, if we just have the null space equal to 0, so if we have no free variables, that means we just have the trivial solution. The null space is equal to just the 0 vector. And that's it. So it's not going to be, there's still one vector in there, so we can't really say that same property as the number of free variables. So that's the null space. Now we're going to look at something that's similar, the column space of a matrix. So the column space of an n by n matrix, we're going to denote it as COL of A, is the set of all linear combinations of the columns of A. So if A is equal to the columns A1 to AN, then the column space of A is equal to the span of those n vectors. Similar to the null space of A, the column space is a subspace of Rm. And recall that if AX is equal to B, then B is a linear combination of the columns of A. That's something that we took care of in the first few sections of Chapter 1. If X equals B, then B is a linear combination of the columns of A. Therefore, another way we can think about the column space of A is that the column space of A is the set of vectors B such that B is equal to AX for some X in Rn. It is the range of matrix multiplication of AX. It's all the different possible outputs I have from A times X. It is the span of the columns of A. So let's look at an example with the column space of A. It's going to be kind of going backwards. Here we're going to have the set W, x minus 2y, 3y, and x plus y, where x and y are real numbers. And I want to find a matrix A such that this is the column space of that matrix. And we're going to do something similar to what we did in the previous section, that we're just going to break up this vector into its different components of x and y. So if I have x minus 2y, 3y, and x plus y, I can rewrite that as a linear combination of x times a vector and y times a vector by just looking at the coefficients in front of the x and y. So for instance, the negative 2, 3, and 1 here come from the coefficients in front of the y variable. And same for the x, I have 1, 0, 1. And therefore, by the definition of matrix vector multiplication, I can rewrite this as the matrix 1, 0, 1, negative 2, 3, 1 times xy, which means that my matrix A is that same matrix, 1, 0, 1, negative 2, 3, 1. So W would be the set of linear combinations of those vectors, 1, 0, 1, and negative 2, 3, 1. Another way to think about the column space is that the column space of an n by n matrix A is all of Rm. So it's not just going to be a subset, but it's going to be all of Rm if and only if the equation Ax equals B has a solution for each B in Rm. We're going to think about the column space as the range, all the possible B's that can get an output of A times X. Column space of A is the range of AX. If I plug in different X's, I get different outputs out, and the set of all outputs there is the column space. We could think about this in the idea of linear transformations, but that is not going to be part of this course, even though we could jump into that realm as well. We'll just quickly say this idea of the range. And sorry, one more point here. The box thing here is saying that the range is equal to the codomain in this case. That all of Rm is the range and not just the codomain. So what's very useful to think about the null space and the column space together and think about how are they similar, how are they different. They're both subspaces, but in a much different kind of form. So let's look at this matrix. This is a 4 by 3 matrix. And we have that the column space of A is a subspace of Rk, where K is going to be equal to 4, that first entry, the M M position. The null space of A is going to be a subspace of RL, where L is 3 in this case, and that is that second space, that second entry. Both subspaces, but they kind of correspond to the different entries in that M by N dimension. Next thing we're going to do is find a non-zero vector in column A. That is, find some vector. There are infinitely many possibilities. In fact, any linear combination will do. Of the columns of A. So you can pick your 3 favorite numbers. How about 1, 0, and -2? Have anything you want. And you could have 1 times 1 plus 0 times 2 minus 2 times 3 is -5. 1 times 2 plus 0 times 4 minus 2 times 7 is -12. 1 times 3 plus 0 times 6 minus 2 times 10 is -17. 1 times 0 plus 0 times 0 minus 2 times 1 is -2. So there is one non-zero vector in column of A. We could find a whole bunch very, very easily. Again, just pick your 3 favorite numbers. Anything will do. The only number that you can't choose is 0, 0, and 0, because then you would just get the 0 vector out. We're looking for a non-zero vector in the column space of A. Note that you can always get the 0 vector in the column space of A, and that's because the column space of A is a subspace, and it should always contain the 0 vector. And again, if we just have zeros as our constants, we'll always get that as an output. Next, we're going to find a non-zero vector in the null space of A. This is a little bit more work we have to do. But again, we're going to do what we did in section 1.5. We're going to take our augmented matrix of the homogeneous system, row reduce, and then look at the solution and find one possible solution in there. So if I row reduce this matrix, this is in row reduced echelon form. We have 2 pivots. We have 1 free variable, which means that I should be able to write the null space as the span of one vector. If we write this as equations, I have x1 is equal to -2x2, x2 is equal to x2, it's a free variable, and x3 is equal to 0. That's for my 2 systems, or 2 equations here. x1 plus 2x2 is equal to 0. x3 is equal to 0. And then I can find one vector in the null space of A by just letting x2, my free variable, be something other than 0, as I'll get the 0 vector out. So let's let x2 be 3. And then x1 is -2x2, so that would be -6. x2 would be 3. x3 would be 0. And there is one solution to ax equals 0, one vector in the null space of A. In general, the null space of A here would be the span of the vector 0, 1, or negative 2, 1, 0. That's coming from the coefficients on the x2 free variable there. So let's take a second and just rewind back to section 4.1 and talk about subspaces again. So a subspace of vector space V is a subset H of V that has the three properties. The zero vector of V is in H. H is closed under vector addition. That is, if you take any two arbitrary vectors in H, their sum is in H. H is closed under scalar multiplication. That is, for each U in H and each scalar C, CU is in H. And if the subset H satisfies all three of those properties, then H is itself a vector space. The next two examples we talk about are going to be about subspaces of vector spaces. And also note that a few things from chapter 4 so far. We know that the span of vectors is itself a vector space. And we know that the null space and the column space are subspaces of Rn and Rm, respectively. So, in section 4.1, we said that in order to determine something as a subspace, we need to show that it satisfies those three properties, or we can show that it's a span of vectors. Now we have two more tools at our disposal. If we can show that it is a null space of some matrix, then it has to be a subspace, or likewise the column space of some matrix. So let's look at some examples now. Determine whether each of the following sets is a vector space or provide a counter example. Again, one counter example will show that it's not a subspace or a vector space. So H is going to be the set of vectors x, y, such that if I take the first entry minus the second entry, I have to equal 4. However, this is not going to be a vector space because the 0 vector, that is 0, 0, is not in H. Why is that the case? Because 0 minus 0 does not equal 4. So therefore, H is not a vector space. It doesn't satisfy that first property of what a subspace has to be. The next example here says, let's look at the vectors x, y, z, and R3 such that x minus y equals 0 and y plus z equals 0. And in order to look at this set, we're going to rewrite x minus y equals 0 and y plus 0, y plus z equals 0, as matrix multiplication, or as a system, ax equal 0. In this case, the first column corresponds to the x's. That's going to be 1 and 0. The second one is going to correspond to the y's. That's negative 1 and 1. And finally, we have 0, 1 corresponding to the z's. This is going back all the way to section 1.1. If I gave you a system of linear equations, you can write that as an augmented matrix or a matrix multiplication. And that's what we're doing here. So, in this case, we have that this x, y, z is the set of all solutions to ax equal 0. So therefore, V is the null space of A. And since the null space of A is a subspace, then we have this is a vector space as well. And let's look at one more example here. The set S, x plus y, 2x minus 3y, and 3y, where x, y, and z are real. We're going to do this in two different ways. One is like we did in section 4.1, that I can rewrite this as the span of two vectors. If I break down all the stuff with x and all the stuff with y, I have 1, 2, and 0 times x, 1, negative 3, 3 times y, and therefore S is the span of those two vectors, and therefore it is a vector space or a subspace. Another way to think about that is we can think about this as the column space of the matrix A, which is 1, 2, 0, 1, negative 3, 3, and therefore it's a vector space because it's a column space. And that's very similar, and since our definition of column space has to deal with the span of vectors, that shouldn't be too surprising that that's happening. Now that we've introduced the null space and the column space, we're going to talk furthermore about those and talk about why they're important. They're not just important just because they're subspaces, they're important for many other reasons. And we're going to start talking about the dimension of a vector space and bases of a vector space going forward.